All right, so now let me go ahead and prove the Taylor theorem with the integral remainder. Taylor's theorem with an integral remainder. So let me first state the theorem precisely. So if you have f is n plus 1 times differentiable in some interval, closed interval from a to b, then for any x and x0, which is in this interval, right, we have that f of x is equal to the sum from k equals 0 to n for involving a sum. It's like, involving the kth derivative of f evaluated at x0 divided by k factorial multiplied into the polynomial monomial term x minus x0 to the k, right? So this is the usual Taylor polynomial of degree n, right, which I denote by Pn of x. Okay, and then there's a integral remainder term, which is the integral from x0 to x of the nth plus first derivative of f at the point t multiplied into x minus t to the nth power over n factorial dt. Okay, and then this is what I call Rn of x. And as we saw before, it's like by some sort of application of a mean value theorem for integral type result, it's like you can rewrite this into sort of the more common expression for the remainder term. It says that the remainder is nth derivative of n plus first derivative of f. It's like multiplied by x minus x0 to the nth plus first power evaluated at some point between x0 and x. Okay, but we're going to start with this remainder result, and we're going to prove this using a combination of the fundamental theorem of calculus as the sort of induction sort of basis, and then we're going to proceed by a induction argument which involves integration by parts. Okay, so let's go ahead and prove this. So the proof is as follows. So we know by the fundamental theorem of calculus that f of x is equal to f of x0 plus the integral from x0 to x of f prime t dt, right? And this agrees with the expression which we have here, which I denote by star. So this agrees with star for the n equals to 0 case. Okay, so that's my induction basis. And so I'm going to proceed by assuming that this holds for n equals L. So I assume that star holds for n equals L, okay, which is to say that f of x is equal to sum from k equals to 0 to n of fk at x0 over k factorial x minus x0 to the kth power plus the integral from x0 to x of the L plus first derivative of f at the point t x minus t to the L power over L factorial dt. And what we're going to show is that when you apply integration by parts to this integral term, you'll get the next term in the Taylor polynomial plus the next higher remainder term. Okay, so what we're basically showing, if you will, is that RL, right, this is the RL remainder term at x, is equal to f L plus 1 x0 over L plus 1 factorial x minus x0 to the L plus first power plus RL1 x. Okay, that's basically what we're going to try to show. Okay, that's more or less what you're trying to show here. Okay, so let me just leave that here and then try to do that calculation. Okay, so you have this integral from x0 to x of L plus first derivative f at t, x minus t to the L power over L factorial dt. And so I'm going to think of this as u, and then this whole thing here as dv. Okay, then with that in mind, du is going to be the L plus second derivative at t dt, and then v is going to be minus 1 x minus t to the L plus first power divided by L plus 1 factorial. Okay, so that's sort of the integration by parts stuff. Okay, so that is equal to, okay, so this is integral of u dv is uv, it's like with the boundary, sort of, you know, it's like with the limits minus the integral of, you know, it's like v du, right? So what you have is u is this and v is this. So you have f L plus 1, L plus first derivative of f at t multiplied into minus 1 x minus t to the L plus first power over L plus 1 factorial evaluated at x and x0. Okay, so what's going to happen is that when you substitute t is equal to x here, that's fine. But when you substitute t is equal to x here, you get x minus x, so that term vanishes. So the sort of the first term vanishes, and so the only term which is non-vanishing is this other term here. Okay, so so that's going to give me L plus first derivative at x0, and then there's going to be another minus sign because I'm subtracting off the value of this at x0, so there's a minus sign squared. And then there's going to be x minus x0 to the L plus first power over L plus 1 factorial. So that term is exactly the next term of the remainder, right? But then there's also the other term coming from the integration by parts. So this integral from minus the integral from x0 to x of the, so this is the u dv, so there's a v du term. So v is minus 1 x minus t to the L plus first power over L plus 1 factorial. And then du is the second, is the L plus 2 derivative of f at t dt. Okay, so the minus 1's again cancel. So this, okay, so this is equal to plus the integral from x0 to x of f L plus 2 derivative of f times x minus t L plus 1 over L plus 1 factorial dt. Right, so that minus 1 squared term cancels. So that's exactly what we want. Right, so the upshot, if you will, is that that means that f of x is equal to the sum from k equals 0 to L of fk x0 over k factorial x minus x0 to the k power plus this term f L plus 1 x0 x minus x0 to the L plus first power over L plus 1 factorial plus the integral from x0 to x of f, the L plus tooth derivative of f evaluated at t, x minus t to the L plus 1 over L plus 1 factorial dt, right, which of course is nothing more than the Taylor polynomial of degree L plus 1 plus the remainder term for L plus 1 as well. Okay, so that proves the theorem which we have. And again, once you have this integral expression for the remainder term, you can apply this mean value theorem for integrals, right, in order to get the more familiar expression where the remainder term is sort of, where the remainder term is like is in terms of the usual expression which we've seen before. Okay, so anyway, so let me just stop here for now.